Okay, this first one here. What do you have for ionic bond definition?
The bond between like a cation and an ion.
There you go. What's the definition not? Metal and a nonmetal. Now, a metal and a nonmetal is definitely an ionic bond, but that's not the definition because you can have ionic bonds that have no metal in them. Prime example would be, say something like that. How do you know that that has no metal in it is an ionic bond? Say again? No, this is an ionic bond. That chlorine is definitely negative. How do I know that this is ionic? Because NH4 is a polyatomic ion, so automatically you've got an ionic bond. Okay. All right, so how'd you guys like the table? Was that fun? Or just boring? Hard, easy? All it is I take something from the top, I take something from the side, and then I match their charges up. If they don't match up, then I make a match up. So that first one is NaCl. It's because what charge does sodium make when it forms, when it goes into a compound? How do you know it's +1? It's in the very first row of the periodic table. Also, you can look on your periodic table and see that the oxidation state for sodium is 1. That's it. If it's in a compound, it can't be 0. It can only have a 0 for a charge if it's by itself. So once it goes into a compound, then it's done something with its electrons, and so charge would be +1. So why is it 1 to 1? Well, if sodium's a +1 and chlorine's a -1, then they just cancel out, and that's it. So the next one, what do I need to do with the sodium sulfide? I need 2 sodiums here, right? Na2S. 2 +1s cancel out that -1. And then you can see the sodium and the nitrate go 1 to 1 together because the nitrate's charge is also a -1. And the sulfate, I'm going to again need 2 sodiums here because the sulfate's charge is -2. Yeah.
So back to the sodium nitrate.
Yeah.
So the overall charge of the nitrate is the negative.
Yep.
But
That's all that matters.
so it doesn't matter that
Doesn't.
there's 3 oxygen.
Well, what happened is the 3 oxygens and the nitrogen together have a -1 charge.
Okay.
So it's not the oxygen is a -2 and a -2 and a -2, and the nitrogen is something. Well, the nitrogen is something. If the oxygens in the nitrate are all a -2, what's the nitrogen's charge? +5.
Okay.
So if I've got an O and an O and an O, and it's a -2 and a -2 and a -2, and this stuff has to equal -1, what's the nitrogen's charge got to be? +5 -6 gives us a -1, so that's what's happened. And if you look on the table, that kind of makes sense with nitrogen. Since nitrogen is the less electronegative atom, it's going to have its electrons taken away. And so what would nitrogen be happy with? Gaining 3 electrons? Why does it want to gain 3 electrons? So it can be neon. Well, what if it lost 5 electrons? Now what is it? It's helium. Is it sad? No, it has an electron configuration that's a noble gas. It would have been easier for it usually to get to neon, but if you've got an element that will take away the 5 outer electrons and get it down to helium, it's fine with that. It couldn't care which direction it goes, just as long as it gets there. So yeah, once you're looking at for these columns here with the polyatomic ions on it, I would just write a -1, a -2, a -2, and a -3, because that's it. It's set. So why is the carbonate going to look a lot like the sulfate? Got the same -2 charge. So this one here, and this one here, and this one here, they're all going to have the same ratios of sodium to anion, because
On the carbonate, it wouldn't be Na2CO6. It would be
Nope.
Only the sodium gets.
Yep. The carbonate's polyatomic ion is CO3 -2. And so that thing, that CO3 minus 2, is a thing with a minus 2 charge on it, and I just need to put on a couple of sodiums to cancel it out.
Okay, that makes sense.
You will never actually change the polyatomic ions charge, or the number of atoms inside the polyatomic ion. We'll see here in a second when we need to change the number of polyatomic ions. So then the last one is Na3PO4. Okay, so this next row is going to look pretty much identical to the first row. How come? Because they both have a +1 charge, right? So this is just going to be AgCl, and this is going to be Ag2S, and this is going to be AgNO3, and this is going to be Ag2SO4, and this will be Ag2CO3, and this will be Ag3PO4. Bless you. Okay, the next row is going to look almost the same as the first two rows. Why? Because ammonium is also a +1. It's going to be a little bit different because I have to deal with the ammonium as a whole, but that's just a couple of parentheses, so let's look at that. So the first one is just going to be NH4Cl. Everybody all right with that one? The next one, I need some parentheses here. A parentheses, NH4 close parentheses S. So what's the deal with that?
Saying there's 2 ammoniums.
Yeah, so I what I'm not writing is N2H8, because that thing, that's not what's really there. Yes, there are 2 nitrogens now and there are 8 hydrogens, but they didn't come however they wanted to. They could only show up as N's with 4 H's on them. So I'm telling the person that 2 ammonium polyatomic ions are there. Because when this thing separates, and when this goes into water, it will separate. It'll separate into 2 different NH4s and an S. So the NH4s will stay stuck together. So then the next one is NH4NO3. And then parentheses NH4 and NH4 2CO3 and NH4 3PO4. All right, so this one, and this one, and this one. So why did I highlight those in the column on the left? They all have a +1. All of them are going to have the exact same ratios as I run down. I'm just changing the letters, but the numbers are going to be staying the same. And what about why are those all blue? Those guys are all going to be +2. And then I've got the aluminum and the manganese who are 3 and 7. So let's do, I'm going to do this copper one right here. So it's CuCl2 because the copper's got a +2 charge and the chlorines are a -1. And then I've got CuS because they both have a charge of 2, +2 and -2. And then I've got Cu parentheses NO3 subscripted 2. Why did I need to put those parentheses in there? I need to put 2 nitrates in there because their charges are each -1, and so I'm going to be required to have 2 of those things, and it's not an N2O6, it's 2 separate NO3s. So that parentheses is just telling you there's 2 of everything inside of the parentheses. And then I've got a CuSO4, and then I've got a CuCO3, and then I've got, how come this last one here, Cu3PO4 2? What's the deal with that? Lowest common number, I have to equal the charges out. So I have 3 coppers, each with a +2 charge, giving me +6, and I've got 2 phosphates, each with a -3 charge, giving me -6. So then they cancel each other out. That's what the aluminum one, well, no, the aluminum one's not going to look like that. So the ones that I have colored in blue, there on the left, Tell me about them. And so this row here that I have for the copper, it's going to be identical for all of these, isn't it? So what I have written here for this copper 2 carbonate, how's it going to look right here for the calcium block? What's going to be different? It's going to be Ca instead of Cu. So all of those ones that are blue are going to be the same all the way across the ratios. Let's do this aluminum one. So AlCl3 and Al2S3. That's terrible. Al2S3 and Al and then NO3 3 and Al2SO4 3 and Al2CO3 3 and then AlPO4. So I'm not going to fill in the rest of these because well, let's do the manganese one just because that's the only one that's different. MnCl7, Mn2S7, MnNO3 7, Mn2SO4 7, Mn2CO3 7, and Mn3PO4 7. All right, so for these ones we have shaded in gray, give me an oxidation number, compound name, and substance. All right, so the one out of column number 1 is HgCl2. So oxidation states, what is it for the mercury? No. Yeah, it was given as +2, and then the chlorine is a -1. And what's the name of this? Mercury 2 chloride. Why do I need the 2?
Because it has different oxidation.
Because it could be a 1. So since it has the ability to have more than one charge, I have to be told what the charge is. So the second one is MgS. And what are the charges here? +2 and a -2. And the name for this one? Magnesium sulfide. How come I'm not saying magnesium 2 sulfide like I did with the first one? There's only one possibility for magnesium. It can only be +2. It's either 0, but if it's in a compound, it's got to be +2 because it's in group 2. So the third one is, what is that? Silver nitrate. So AgNO3. And the charge on the silver is a +1. And the charge on the nitrate is a -1. And it's silver nitrate. So silver is a transition metal. It's below copper. How come I don't say silver 1?
Because you already know because of the nitrate.
No, not because I already know because of the nitrate. Because if it was silver 2, I'd still say silver nitrate. It's only got one possibility. That's the answer always. If there isn't a parentheses telling you what the charge is, it's because the thing doesn't have a charge that can be any different than what it is. And we talked about it on Thursday that the zinc, the cadmium, and the silver, those 3 are transition metals and they're kind of touching each other there. And all 3 of those have a set oxidation number. So the cadmium and zinc both have a +2. So you'll never say like cadmium 2 or zinc 2. And the silver always has a +1, so you'll never say silver 1. Nick.
Because you asked for each atom, wouldn't you want?
Oh, did I ask for each atom? Did I say that? Oh yeah. Yep, you're right. I asked for each atom. My bad. So on this one, I would want nitrogen with a +5 and oxygen with a -2. Yep. fourth one. Copper sulfide, okay, so CuSO4. And so my copper's got a +2 charge. My oxygen's got a -2 charge, and my sulfur's got a +6 charge. And then this is copper 2 sulfate. NH4CO3. NH42CO3. Okay, my hydrogen is a plus, and my nitrogen is a -3, and my oxygen is a -2, and my carbon is a +4. Let's make sure that's right. So I've got 6, -6, and -3, and I've got 4 +1s, and I've got +4. No, that didn't look right. What did I do wrong? Okay, so that's correct. And O -2, it's a +4. Yeah, that's right. Okay. You might find it difficult to determine the oxidation states for a compound with 2 polyatomic ions in it, but the nice thing about the polyatomic ions is you don't have to leave them in the molecule. So instead of me looking at what the nitrogen's charge is inside of this whole molecule here, I know that polyatomic ion's there. So what are the charges inside that polyatomic ion? I know the hydrogens are a plus charge because they're with a nonmetal, and there are 4 of them, so it's 4 pluses, and then I need to cancel out 3 of them, so then the nitrogen is a -3. Just because it goes into a compound doesn't mean that those charges are going to be different, so they stay the same because it is a little thing. And so the charge on the nitrogen will be a -3 no matter what, and the charge on the hydrogen will be a +1 no matter what, if it's in a compound or not in a compound. So then I just determine the charges on the nitrogens and the hydrogens, and then I can look at my carbonate. So my carbonate, I have oxygens with a -2, so that gives me -6. I need to have a leftover -2, and so that means the carbon's charge has to be a +4. And since that works for this polyatomic ion and that works for this polyatomic ion, then it's going to work for the molecule. And name for this one? Ammonium. You never need to modify the names of the polyatomic ions. You just say their names, that's it. Doesn't matter how many there are. So in this case, there were 2 ammoniums. Doesn't modify the name that it's still ammonium. Just leave it. So remember, the only reason we put the parentheses 2 or parentheses 3 is because the charge varies. Is the charge on the ammonium ever going to vary? No, it's always a +1, so I don't need to worry about it. And what was the last one? All right, K3PO4. All right, so the charge on the potassium is a plus. The charge on the oxygen is a -2. And so then the phosphorus must have what charge? +5? Yep. 3 and 5 is 8, and 4 and 2, 8. Yep, totally. And the name for this one?
Potassium phosphate.
Okay.